Hello, my name is Martin Berg. I'm a faculty member in the Mechanical Engineering Department at the University of Washington in Seattle. I teach a course each spring quarter in digital control system design to graduate and advanced undergraduate students. And in this video, I will introduce you to some of the hands-on with hardware projects I've developed for my students in that course, all of them utilizing the myRIO. First, I want to make it clear that by a digital control system, I mean a sample data system comprised of a continuous time or analog plant controlled via a discrete time control law that's implemented on a digital computer. So for these hands-on with hardware projects, we needed to come up with an analog plant. A traditional choice would have been something along the lines of perhaps an inverted pendulum, which certainly could be obtained commercially. A disadvantage to that approach, in our view, is number one, it's costly. Number two, the hardware setups are decidedly not portable. They need to reside in a laboratory somewhere. That necessitates our students coming to campus to have a true hands-on with hardware experience. In particular, for our distance learning students, that is not possible. The approach we've taken to realizing the analog plant for each of the projects we assign to our students is exemplified by what you see in this slide. It's a simple circuit wired up on a breadboard using an op-amp chip and some R's and C's. This happens to be a second order example. The advantages of such an analog plant are several. It's compact, the cost is low, less than $10. Each student builds his or her own analog plant. The op-amp chip is an active chip. It requires plus or minus 15 volts and a ground. Each of those can be supplied by the corresponding pins on the myRIO directly. The circuit, as it's wired up, is high input impedance and low output impedance. Consequently, the input to the circuit can be driven directly by any of the analog output pins on the myRIO, and the output from the circuit can drive any of the analog input pins on the myRIO. Consequently, no driver software whatsoever is required to operate this plant. With that introduction to the approach we took to realizing the analog plant for each of our projects, we'll move on now to discuss some specifics. Here we see the pinout diagram for the op-amp chip, the point being that the chip implements 4 approximately ideal operational amplifiers. This slide shows a schematic diagram of the second order plant that's on the breadboard on the previous slide. Voltage follower circuits at the upstream and downstream ends yield infinite input impedance and zero output impedance for the circuit as a whole. Sandwiched between the followers is a subsystem having standard form second order dynamics with natural frequency omega n1 and damping ratio zeta 1. And from the given formulas for omega n and zeta, it's apparent that choosing R1, R2, C1, and C2 values to realize a particular natural frequency and damping ratio is quite straightforward. The particular R and C values we chose are indicated here. They yield a natural frequency omega n1 and a damping ratio zeta 1 near 1 Hz and 10% respectively. And finally, this last addition to this slide points out that from the sampling theorem, the absolute minimum sampling rate to enable control of this plant's vibration mode is very close to 2 samples per second. The analog plant in this slide is the one I first have my students close a feedback loop around. In that project, I have them implement the backwards difference approximation to continuous time derivative feedback alone, and that enables them to dramatically increase the damping ratio of the closed-loop system's vibration mode. In the following project, I have them complete a model-based direct Z-plane root locus design of a PID controller for the same plant to meet specific reference step response and disturbance step response performance objectives. And I, of course, have them implement their design hardware in the loop with their analog plant. But rather than show you those results, I will instead move on to show you some results from some work I have them do later in the quarter with a fourth order analog plant. A breadboard realization of that plant is shown in this slide. As a practical matter, This circuit is complicated enough that too many of our students spend too much time struggling to get it wired up successfully. In the light of that, the fourth order plant that our students will make use of this quarter is shown on this slide. It's a printed circuit board rendition of the breadboard circuit on the previous slide. Its cost per unit in a 100 unit lot size remains under $10. And by retaining the circuit's R-out num, R-out den 1, and R-out den 2 resistors as to be inserted by hand, much of the reconfigurability of its breadboard equivalent is retained. The schematic diagram for this plant is shown in this slide. It's a parallel combination of two standard form second-order systems subject to a control input U and a disturbance input D, and it produces one output signal Y. The system's input-output dynamics are shown in the Laplace domain here, with the system's transfer function written in a partial fraction expanded form. That the system implements a parallel combination of two vibration modes is evident, with the natural frequencies and damping ratios of those modes being omega n1 and omega n2, and zeta 1 and zeta 2. The R1 through R4 and C1 through C4 components we chose produced vibration modes at 1 Hz and 20 Hz and damping ratios of 10% and 5% respectively. The R-out num, R-out den 1, and R-out den 2 components we chose produced an influence factor for the 1 Hz vibration mode that was a factor of 10 larger than for the 20 Hz mode. And the Rn num, Rn den U, and Rn den D components we chose were all equal to produce unity multipliers on the system's control and disturbance inputs. Having finally reached this point, we'll next look briefly at some results. This slide shows the response of the uncontrolled fourth-order analog plant to a step input. The 1 Hz 10% damping mode is dominant, and the 20 Hz 5% damping mode also appears. This plot is from a direct Z-plane root locus PID controller design for the same analog plant at 20 samples per second. It plots the closed-loop poles versus an increase in the derivative control gain Kd. The analog plant's 1 Hz vibration mode poles start out here and here for Kd equals 0, and migrate to here and here for Kd equals 0.3. It is crucially important to realize that with the sampling rate at just 20 samples per second, the analog plant's 20 Hz vibration mode poles are aliased in this figure. They start out here and here for Kd equals 0 and migrate to here and here for Kd equals 0.3. The Simulink predicted response of the PID-controlled closed-loop system to a reference step input is shown in this slide. It matches up remarkably well with the hardware-in-the-loop response that's shown in the next slide. In this slide, the top graph plots in red the response data points collected at 1,000 samples per second, and the bottom graph plots, also in red, the response data points collected at the sampling instance. Note the loss of information about the analog plant's 20 Hz vibration mode in the sample data. And one final question. Suppose it suddenly became important to do all of the above and do a better job of not exciting the analog plant's 20 Hz vibration mode. Well, faster sampling is always better, right? So what happens if we double the sampling rate? It turns out that in this case, doubling the sampling rate causes the closed-loop system to be unstable. Why is that? It's an important practical question, and it gives rise to an extremely valuable learning opportunity for our students.